In this lesson, we're going to have a look at something called the double angle formulae. Now, these are just basically alternative versions of the addition formulae that we looked at last lesson. But rather than talking about A plus B, we can look at 2A, or we can think of that as A plus A. So I've got the three addition formulae there that we used last lesson. And I'm going to use these to find sine 2A, cos 2A, and tan 2A. Now, like I said, sine 2A, that is the same as A plus another A. So we could rewrite this as sine A cos, then it's going to be cos A as well, plus cos A sine A. If I simplify that, then this is the same as 2 sine A cos A. If we do the same process for cos 2A, this is going to be cos A times cos A, minus, because remember when it's a plus, this becomes a minus in the middle, sine A sine A. If I simplify that, this is cos squared A minus sine squared A. And last of all, for tan 2A, this is going to be tan A plus tan A on top. And on the bottom is going to be 1 minus tan A tan A. So when I simplify this, on top I will have 2 tan A over 1 minus tan squared A. And these three are called the double angle formulae. Now these have got several uses, and we're going to show you a fair few of these in this lesson. But we could come up with other formulae as well. We could come up with something like sine 3A or sine 4A and so on by using the same kind of idea. If I wanted to come up with an expression for sine 3A instead, rather than making it A plus A, I could rewrite this as sine 2A plus A. And then I could come up with an expression for that. So that would then be sine 2A cos A plus cos 2A sine A, and so on. And then I could actually expand this using this formula here, and so on. I could come up with expressions for sine or cos 4A if I wanted to, by writing it as sine 2A plus 2A. Okay, and so on. And you can keep going with this. And you can come up with all sorts of formulae for these sort of expressions. Now, the most useful out of these three is probably cos 2A. So I want to focus on that one a little bit more. So cos 2A is cos squared A minus sine squared A. And the reason that this one is useful is because you can change between cos 2A and then functions with a squared in, which is quite useful because sometimes you want to deal with functions with a squared and sometimes you want to deal with them without a squared. For example, without a squared, this is a lot easier to differentiate and integrate that you'll learn about later on. Differentiating and integrating things with a squared in is a bit more complicated. However, I might want to actually include squared because a lot of my identities talk about cos squared and sine squared. So it's quite useful to have a formula that allows me to swap between these two things. Now, we can also use this to write it just in terms of cos or just in terms of sine. So if I wanted to write this expression just in terms of cos, I could write cos 2A is, I'll leave the first term alone, cos squared A, minus, then instead of sine squared, I could rewrite that as 1 minus cos squared A. So I could say that cos 2A is 2 cos squared A minus 1. And that's quite nice because it links cos and cos squared. Likewise, I could try and write it with just sine squared. So I can replace the cos squared with 1 minus sine squared. And then simplify that. So I get 1 minus 2 sine squared A. So these two forms are also really useful because, yeah, they let you swap between cos squared and cos, or they let you swap between sine squared and cos 2A. When we come on to integration later on, these two formulae are particularly useful for integrating cos squared and sine squared. So similar to all the examples that we did last lesson, I've got some expressions here that we're going to try and simplify. So the first one, cos squared 50 minus sine squared 50. I've got the formula here. This looks a bit like the formula for cos 2x. So let's just rewrite this one. Cos squared 50 minus sine squared 50. I could rewrite this as cos of 2 times 50, or cos of 100. So cos 100 is actually equal to this, using our double angle formula for cos. Part B, 2 tan pi over 6 over 1 minus tan squared pi over 6. Well, this obviously looks like the double angle formula for tan, but instead of x, I've got pi over 6. So this is equal to tan 2 times pi over 6. Well, that is tan pi over 3. So we can say that those two are equivalent. This last one, 4 sine 70 over sec 70. Maybe let's just start by writing this one a bit differently. So this is 4 sine 70 times 1 over sec 70. Okay, that's the same as dividing by sec 70 is timesing by 1 over sec 70. Now, 1 over sec 70, that is cos 70. So this is actually 4 sine 70 times cos 70. Now this format looks a little bit like this one here for sine 2x. The only difference is it's got a 4 at the front rather than a 2 at the front. So maybe to make this more obvious, let's factor out a 2. And now you can spot the bit in the bracket looks just like the double angle formula for sine. So this is going to be sine 2 lots of x, or sine 2 lots of 70. So our answer is 2 sine 140. So being able to spot what format they look like is really useful for simplifying or rewriting equations. Okay, let's have a look at some more. I'm going to try and simplify these and rewrite them. So the first one here, the square root of cos 2x plus 1. Let's see what we can do with that. So I'm just going to use my double angle formula to expand it. So this is going to become cos squared x minus sine squared x plus 1, all square rooted. Now that's not very easy to simplify. I can't just square root everything in here. Okay, that's not how square rooting works. Okay, if you have 25 plus 36 and you square root the whole thing, you do not get 5 plus 6. That's not how it works. Okay, it's not 11 squared. Okay, so we need to try and simplify this a bit more. I think what I'm going to do is I'm going to swap out the sine squared for a 1 minus cos squared. So instead of sine x, I'm going to have 1 minus cos squared x plus 1. Just because then I'll have it in terms of just one function. So now I've got cos squared minus cos squared. So that's 2 cos squared x. And then I've got minus 1 plus 1. So they eliminate each other. So I'm just left with this. And I suppose I could rewrite that as root 2 times cos x. There we go. Root 2 times cos x would be another way of rewriting that. Okay, let's look at question E. Sine cubed x cos cubed x. Okay, if I want to try and rewrite this using my double angle formula and just in terms of one function, let's start by just writing it sine x cos x all cubed. Okay, now sine x cos x, that is one of my double angle formulae, or similar to one of my double angle formulae anyway. Sine 2x is 2 sine x cos x. So just sine x cos x, well, that would be half of sine 2x. So I can rewrite this as half of sine 2x cubed, and then I can cube it. So this is going to be 1/8 of sine cubed 2x. So that's how I can rewrite that one in terms of just one function. F. Okay. So 8 cos x sine x times cos 2x. Well, we've got this sine x cos x pattern in here again. Okay, so that's this addition formula up here, or this double angle formula up here. Let's make it look more like sine 2x. This is 4 times 2 sine x cos x. We'll deal with the cos 2x bit in a minute. So this is then 4 times, instead of 2 sine x cos x, I can just write sine 2x. Okay, so now I'm left with 4 sine 2x cos 2x. Now it's still in terms of two functions, so hopefully I can try and simplify it a bit more. Again, we've got this same pattern, sine x cos x again. Yes, it's 2x, but it's still that pattern of sine x cos x. So again, we're going to try and use this top formula here. I'm going to factor out the 2. So this is 2 sine 2x cos 2x. So this is 2 lots of, instead of 2 sine 2x cos 2x, I could rewrite it as sine, but it's not going to be 2x because it's just whatever this angle here is doubled. So it's going to be sine 4x. So my answer is 2 sine 4x. Okay, it's quite a nice one. Get to use that same pattern twice. Okay, now the last one, G. Okay, for G, 1 minus 4 sine squared x plus 4 sine to the 4x. When I'm looking at this, I'm thinking that this must have come from some sort of expansion. It looks a bit like if I had maybe 1 minus 2x all squared, because that would give me 1, then it would be minus 4x and then plus 4x squared. It's kind of like that pattern there. So I think this has come from an expansion of 1 minus, I guess, 2 sine squared x all squared. We can check that. So 1 minus 2 sine squared x. 1 minus 2 sine squared x. So this is going to be 1 minus 2 sine squared x minus 2 sine squared x, and then plus 4 sine to the 4x. So that works for that one. Now it's a little bit simpler. 1 minus 2 sine squared x, hopefully this should ring a bell, but this is cos 2x. This is one of our forms where we've rearranged it before. So when we looked at these here, cos 2a was 1 minus 2 sine squared a. So this is just going to be cos 2x squared, or cos squared 2x. So it's really handy if you can spot things like this. If you can't, then you could use some of your other identities to rewrite this. Or perhaps a good place to start is normally just writing down all of your identities. So writing down basically what's in this box here, it might help you. But you could do it via a longer route. You could swap this out for 1 minus cos squared and so on. And eventually you could get to something that looks like cos squared minus sine squared, which is a bit more obvious that it's this. Okay, here's a slightly different type of question using these formulae. So given that x is 3 sine theta and y is 3 minus 4 cos 2 theta, eliminate theta and express y in terms of x. So here we've got 3 variables. We've got x, y, and then we've got theta. We want to just try and write it y in terms of x. Okay, so we don't really want theta involved. So this means y equals blah, 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 with an x in it. Okay. This is actually an example of something called a parametric equation, which we'll study later on in the course, which is basically where you describe your y and x coordinates separately in terms of some other parameter. So here we've described our y coordinates and x coordinates in terms of theta, and it lets us draw some more interesting graphs, but we'll talk more about that later on. So to try and rewrite this, maybe this right-hand one, y equals 3 minus 4 cos 2 theta. Let's expand that cos 2 theta. So it's going to become cos squared theta minus sine squared theta using my double angle formula. Now here I have got a link between x and y because I've got sine squared and x is 3 sine theta. Maybe we'll rewrite x as x over 3 equals sine theta, which would then mean that x over 3 squared would be sine squared theta. So I could substitute that in here. The other thing that I would need to do is change this cos squared to something in terms of sine squared as well. So let's do that at the same time. So we've got 3 minus 4 lots of 1 minus sine squared theta minus sine squared theta. Okay. And now what I can do is wherever I see a sine squared, I can replace it with x over 3 squared. So this is basically the point where I'm actually eliminating theta. So I've got y equals 3 minus 4 lots of 1 minus 2 times x over 3 squared. Okay. Now we can try and simplify this a bit more. So this is 3 minus 4 lots of, in the bracket I've got 1 minus, this would be 2x squared over 9. And then, well, I've effectively done it, but it's just about rewriting this in a bit of a nicer way, I think, really. And that would be plus 8x squared over 9. So y is 8x squared over 9 minus 1. Okay, and that is y in terms of x. So you're looking for something that links x and y together. Here it was, well, x talks about sine theta, so I can therefore find sine squared. So if I can try and change this to just talk about sine squared, then I can substitute this in. And we'll do more questions like that when we come to do parametric equations. Okay, something else to be aware of is half angle formulae. So we've talked about double angle formulae, and those are in front of you here. But the half angle formulae obviously talk about what happens when it's a divided by 2 rather than 2 times a. So if we were to look at sine a instead, okay. So here, this angle is twice these ones. So if I was to just look at sine a, then that would be equal to 2 sine a over 2 cos a over 2. Okay, so it's basically exactly the same as this formula here, except I've just swapped the a out for a over 2. The important thing to notice is that this angle here is twice this angle here, which is still true in this statement here. And sometimes this is useful if you've got an expression that talks about an angle divided by 2. We could do the same for cos a. We could write that as cos squared a over 2 minus sine squared a over 2. Likewise for tan, we could write tan a is 2 tan a over 2 over 1 minus tan squared a over 2. Okay. So for example, this statement here, well, this is basically the same formula I've written here, but this would be equal to then just tan a, or in this case, tan theta. So sometimes those are useful. It's more just something to be aware of. They will sometimes come up. Okay, you should be able to have a go at questions 7 to 12 from exercise 7C now, which are similar questions to the ones that we've done before. I want to cover one last bit, which is about using the double angle formula to solve some equations. Now, I might not actually do the solving bit here, but it's more the rearranging that's important, because we've done lots of solving equations in the past. So in this first example, we've got 4 cos theta minus 30 equals 8 root 2 sine theta between 0 and 360. Now, the important bit here is just the rearranging. So let's expand this using our addition formula. And this isn't going to use a double angle formula, this is just going to use an addition formula. So this is going to be cos theta cos 30 plus sine theta sine 30 equals 8 root 2 sine theta. Now, the parts in here which are numbers we can work out. So cos 30 is root 3 over 2. So this is root 3 over 2 cos theta. Sine 30 is a half, so this is half sine theta. So that looks a little bit better already. Now I'm going to times it all by 4. So I've got 2 root 3 cos theta plus 2 sine theta. And then that still equals 8 root 2 sine theta. Now I've got sine and cos here. I could really do with it just being in terms of one function. And unfortunately they're not squared either, so I can't use sine squared plus cos squared equals 1. But hopefully I'll be able to use sine over cos equals tan. So I'm going to move all of my sines together and all of my coses together. So I'm going to leave this 2 root 3 cos theta alone. And I'm going to subtract 2 sine theta from both sides. So on the right hand side I'm going to have 8 root 2 minus 2. Lots of sine theta. And now I'm going to do this last step. I'm basically going to do 2 steps in one. I'm going to divide both sides by cos, because then I'll get sine over cos, which is tan. And I'm going to divide both sides by this bracket here. So I'm going to get 2 root 3 over 8 root 2 minus 2 equals sine theta over cos theta, which is tan theta. And now once we're at this point, we can solve it as we would do normally. So you could do inverse tan of that and then find your multiple solutions. So in this next one, we've got 3 cos 2x minus cos x plus 2 equals 0. So again, let's start by just expanding out this double angle bit. So I've got 3 lots of cos squared x minus sine squared x minus cos x, and then plus 2 equals 0. Now, again, if we're going to try and solve this equation, we need it to be in terms of just one function. So I'm going to swap the sine squared for a cos squared. So it's going to be cos x squared minus 1 minus cos squared x. Now I'm going to expand this. Actually, no, I'm going to simplify the bracket first. So that'll be 2 cos squared x minus 1. Now you could go straight from the top to this third line. If you can remember that this, or the cos 2x function, you can also write as 2 cos squared x minus 1. But if you can't, then you can do these steps like I did. Let's expand this out. So that'll be 6 cos squared x minus 3 minus cos x plus 2. Then we can just simplify it. Okay, so we've now got a quadratic in terms of cos. We can solve that however you like. You could factorize it, or you can use your calculator to help you. So this would give me cos x equals 1/2, or cos x equals minus 1/3. And then we could solve them from there. So we could do inverse cos of this and then find your multiple solutions. For this next one, we've got 2 tan 2y times tan y equals 3. And we've got to solve it between 0 and 2 pi. So let's expand this with a double angle formula. So this is 2 times, and then tan 2y, that is equal to 2 tan y over 1 minus tan squared y. And then we've got to times it by tan y again, and then that equals 3. So if we rewrite this, we've got 2 times this fraction and also times tan y. So that would give me 4 tan squared y over 1 minus tan squared y. equals 3. So we've already got a function which is just in terms of tan, which is quite nice. So it's just about rearranging it into a format which is nicer to solve. So I'm going to times both sides by the bottom of this fraction. So that'd be 3 times this, which is 3 minus 3 tan squared y. Now I'm going to add 3 tan squared y to both sides. So that's 7 tan squared y equals 3. And then divide by 7. So we've got 3 over 7. So this means that tan y is going to be positive root 3 over 7, or tan y is going to be negative root 3 over 7. And then we can do inverse tan of those two and find our multiple solutions. So for the first part of this question, it says, by expanding sine 2a plus a, show that sine 3a is equal to 3 sine a minus 4 sine cubed a. Now we spoke about this earlier on. We can rewrite sine 3a as sine 2a plus a, and then use our addition formula. So let's start with that. So we've got sine 3a, and I can rewrite that as sine 2a plus a. Now if I apply my addition formula, this is going to give me sine 2a cos a plus cos 2a sine a. And now what I can do is I can expand these double angle bits using my double angle formula. So this is then going to be 2 sine a cos a times this other cos a plus cos squared a minus sine squared a times sine a. Now the thing that I'm aiming for has only got sine involved. So I need to try and change any coses back to sines. So here I've got cos a times cos a. This is obviously going to give me a cos squared a. And I'm going to swap the cos squared for 1 minus sine squared. So this is 2 sine a. Then instead of cos squared, I'm going to write this as 1 minus sine squared. In here, I'm going to swap this cos squared for a 1 minus sine squared as well. Okay, and then I'm going to expand this and simplify it. So if I expand this here, I'll get 2 sine a minus 2 sine cubed a plus, let's just simplify this bracket, 1 minus 2 sine squared a times sine a. And I'm just going to expand this last bracket. Just going to leave this bit here as it is. Right, so expanding this, I'm going to get sine a minus 2 sine cubed a. And then just grouping this all together, I will then have 3 sine a minus 4 sine cubed a, which is what we were after. Okay, there we go. So we've proved that sine 3a, you can actually rewrite it like that. And our starting point was to use sine 2a plus a and an addition formula. For part B of this question, we've got to try and solve an equation. And it says hence or otherwise, so that means using your previous working, or you could do it another way, but normally if they say this is going to be easier to use what you've just done. Solve this equation here. Okay, so 16 sine cubed theta minus 12 sine theta minus 2 root 3 equals 0. But we haven't really got this explicitly here, but we've got something similar, haven't we? We've got 3 sine a and minus 4 sine cubed a. So we don't really want this this way around. We ideally want it with a positive sine cubed and a negative sine. So let's just write down what minus sine 3a would be, because that would look more similar. That is then 4 sine cubed a minus 3 sine a. So that looks a little bit more useful in terms of the signs match up. But instead of 4 sine cubed, I want it to be 16. So I just need to times it by 4. So minus 4 sine 3a would be 16 sine cubed a minus 12 sine a. So this is going to be more useful. And I can swap this bit here for minus 4 sine 3a. So the equation that they've asked me to solve, this first bit I can now rewrite as minus 4 sine 3 theta, and I've still got minus 2 root 3 equals 0. And now I've just got to solve this. So that's using what we've just proven to help us out. So I'm going to have then sine 3 theta equals minus 2 root 3 over 4. Or you could write that as sine 3 theta equals negative root 3 over 2. And then we can solve that equation as we would normally. This one's got 3 theta, so you might want to do a substitution maybe to work this out. But we can then solve it between our limits between 0 and 2 pi. Okay, one last one. So now 3 sine 2x equals cos 2x. Now, because of the questions we've just done, your first instinct might be to do use the double angle formulae and expand the left and expand the right and do some simplifying. However, don't jump into these questions too quickly. I've picked this one to illustrate. Sometimes there's a simpler way. Here, we could rearrange this to give me 3 sine 2x over cos 2x equals 1. So that means that tan 2x would then be 1/3. And then we can solve it from there, which is obviously much, much simpler than expanding the left and expanding the right and trying to reduce it down. So just because you see a 2x, don't always jump in and do double angle formulae. There might be a nicer way of doing it. Okay, so if you want to just practice doing some solving, like the questions we've just done, have a look at exercise 7D, and I've picked out questions 1, 4, 7, and 9. Those would be good questions to work on.